Hello everybody, welcome to Investigation 4.1. This is Introducing Exponential Decay. So before we were using the word growth with exponents and we were seeing things go up, up, up. And if we know what decay means that things are getting eaten away, and so I imagine we're going to see things going down, down, down. So here's our focus question. How does the pattern of change in this situation compare with the growth patterns we've studied in previous problems? And then how does the difference show up in a table, a graph, and an equation? So let's dive in. Here we go. Here is a nice little fake situation. Miss Sandy, she enjoys the art of paper folding or origami, but today she decides that she doesn't want to make a crane. Instead, she wants to see how big the areas are of rectangles and squares if she folds the paper over and over again into thirds. If she begins with a piece of paper that is perfectly square at 81 centimeters squared, that's what should be here, squared, determine the size of rectangles of paper or squares after each set of folds. So, thinking about this, we begin at 0 folds. We have 81 centimeters squared. Now, after 3 folds, one of these rectangles is going to be 1/3 of 81. So 1/3 of 81 equals 27 centimeters squared. Cool. Let's keep going. She makes another set of folds. Here's 3 folds now, and if we're just looking at one set of these 3 folds, if we notice that she's folding back and forth, which is perfectly fine, we now have that 27 that we initially had before has now turned into 1/3 of this size. So here we go. 27 times 1/3, or 1/3 of 27, equals 9 centimeters squared. She then does it again, and she'll do it again and again, and we have essentially 1/3 of 1/3 of 1/3. So now we have 1/3 of 1/3 of 9. What is 1/3 of 9? So 9 times 1/3, that would equal 3 centimeters squared. So if she were to do this again and again and again, let's actually figure it out for 10 total sets of folds. And let's actually make a table. So how does the area of the resulting rectangles or squares change with each fold? So let's do a little bit of this math. Let's make a table. So we start out with our folds, and we have our area. And to start out with, we have 0 folds happen, and we had 81 centimeters squared. After 1 fold, we had 27. After 2 sets of folds, we had 9. After 3 sets of folds, we have 3. 4 sets of folds. So if she were to fold all of this again, so fold it all again, and essentially go all the way across and fold it again and have those little tiny squares, we have 3 centimeters squared that has just been turned into 1 centimeter squared. So after the 4th fold, we have 3 times 1/3, or 1/3 of 3, which is 1 centimeter, and so on. And so let's continue this. Let's try 5 and 6, and if we have space over here, we'll do 7, 8, 9, and 10. So I'm going to do a little bit of math magic and fill the rest of this out and see what we get. So the decay is happening. We can see that after each of the folds, she progressively gets 1/3 smaller and smaller and smaller. So let's find out what our growth rate is. And I suppose we don't necessarily want to call it our growth rate. Let's call it maybe our rate of decay, or our decay factor. I suppose we should call it decay factor. Let's figure that out. I'm going to change my spelling of decay. Let's figure out our decay factor. So going from 81 to 27, I could multiply by 1/3, or we could look at this as dividing by 3. Now, let's see if that's the same. From 27 to 9, we could multiply by 1/3, or we could divide by 3. Same thing from 9 to 3. We could multiply by 1/3, or we could be dividing by 3. This is an either or situation. It's not an and. So 81 divided by 3 gets me 27. 27 divided by 3 gets me 9. 9 divided by 3 gets me 3. 3 divided by 3 gets me 1, and so on. And then we can get down into 1/3, 1/9, 1/27, 1/81, 243rd, 729th. Kind of crazy. So from there, let's write an equation that represents this situation. So thinking about our past equations that we've written for exponential growth, we've had this format. We've had y is equal to a times b raised to the x power, where y is our output. This is what comes out. X is our input. That's what goes in. But a and b are constant numbers that we can count on, and there's a multiplication that happens between them. So first of all, our y, our output, is our area. That's what we're finding out each time. So I'm going to put a. As well, our x in this situation is the number of times we are folding it, or the number of sets of folds that we're doing. So I'm going to call that f. Now we need to figure out an initial value, which is typically our a. So what is our y-intercept? What are we putting in there? Where would this graph be crossing our y-axis? And we know that's happening wherever x is equal to 0. So in this case, when folds are equal to 0, how big is the paper that we start out with? 81 centimeters squared. You should be shouting out. And then what are we doing every single time? This operation that's happening in between a and b is typically a timesing. Well, actually, it is a timesing. There's no typically. It is being multiplied. So we have a multiplication happening here. How are we multiplying each and every time? We're multiplying by 1/3. So instead of us having a whole number or something greater than 1, this time we have something that's less than 1 as our growth factor or our decay factor. So that's telling us that we are going to continually get an answer that's smaller and smaller and smaller by a certain amount. That's kind of cool. So let's look at all of this so we can kind of see it all and take it all in. And let's ask ourselves this question. How is this pattern different from past exponential relationships? Well, it's different in that before, in growth relationships, our growth factor was greater than 1. In this situation, decay, our decay factor is less than 1. So essentially, our decay factor is going to be 0.9, 0.8, in this case 1/3, or 0.333 repeating, but it's going to be less than 1. But how is it similar? Let's think about this. How is this similar? Well, it's similar because I still can use the same equation. I can use that y is equal to a times b to the x. Let's graph this information. Let's see what happens if we graph it. So let's go over here to our graph paper that just magically appeared, and let's start out with creating a little bit of a scale factor, or like scale along the bottom. I'm going to say 1, we got 2, oops, that's a bad line, 3, 4, 5 sets of folds. Usually we've noticed that we can typically see things happening in a smaller sort of sets. Ooh, I've totally renumbered the bottom of this completely wrong. 3, 4, 5, and I'll add a 6 here. We can usually see it in a smaller area. So let's see if we can also create a scale along the top that works. So now I have a scale of 0 through 100, so it's going up by tens. Let's start out with our very first point that we're going to plot. We have 0, 81 for our first point, so I'm going to add that in there. It's going to be somewhere in there. We have 127, so it has already dramatically decreased. 2, 9, also dramatically decreased again. 3, 3, 4, 1, 5, a third, so we're getting really close. If I look at this, this reminds me of a function that we have already kind of looked at. The only thing that I see that's different is that it has a y-intercept. If you remember, we've already been looking at things called inverse variations. But I'm going to challenge you to find why this is not an inverse variation and why it's an exponential decay function. So either way, we have a graph, and I can see in this graph that it is fairly similar to our growth graphs in that it has a drastic change in it, like it's drastically declining, whereas the other one was drastically increasing. Our past ones have gone up substantially like that. This time we're drastically declining, so it's not quite this situation, but we're seeing a drastic decrease that's similar, and difference is it's declining instead of getting bigger. So, playing around with this concept, I'd like you to finish the investigation 4.1 investigation. It is A through E. You're going to do all of it. Investigation 4.1, A through E. And I want you to play around with that whole idea. And then after that, do the homework. Enjoy.